Yeah, Dr. Prasad, you can start.
Okay, fine. So good morning to all the esteemed members of the Ocean Society of India, ladies and gentlemen. The Ocean Society of India has taken up the initiative to conduct invited talks as part of the OSI webinar series once in every month. And this talk is arranged from eminent scientists, engineers, academicians working in the broad areas of atmospheric and oceanic sciences, ocean engineering and technology, etc. This webinar series is targeted mainly for students, researchers, scientists, engineers, and working professionals in the field of atmospheric oceanic sciences, ocean engineering and technology disciplines, with a motive to impart and improve the knowledge benefiting the OSA community. I thereby earnestly request all the members to actively participate and get involved in all the lectures under the OSI webinar series that would be held once every month. On behalf of the Ocean Society of India, it is my proud privilege to welcome Professor Naresh Visa, Assistant Professor Grade 1, the Department of Earth and Atmospheric Sciences, NIT Rourkela, for the invited talk today. So Professor Naresh will be delivering a talk on the topic Tropical Ocean and Atmosphere Interactions, a topic of immense interest, especially in the field of air-sea interaction and allied areas. Professor Naresh has completed his master's degree 2006-2008 in meteorology from Andhra University, Visakhapatnam, and PhD from 2009 to 2013 in atmospheric sciences from IIT Kharagpur. As a co-supervisor of his PhD work, I personally know Professor Naresh very well since his PhD days at IIT Kharagpur. So he is a very serious researcher having a strong background in atmospheric and oceanic sciences. He is a dedicated scientist having a strong flair with a proven track record and very impressive list of publications in peer-reviewed journals that demonstrates his special skills and ability in the field of research. So after completing his PhD, he joined as a postdoctoral fellow at the Center for Water, Law, Policy and Science at University of Dundee, Scotland, UK, during the period from March 2013 to February 2014. Thereafter, he worked as a senior research associate at Lancaster University, UK, from March 2014 to December 2014. So in the end of December 2014, Professor Naresh has joined in the Department of Earth and Atmospheric Sciences, NIT Rourkela, as assistant professor and continuing working there. His research interests are varied on topics like modeling of ocean and atmospheric interactions, climate change and modeling of extremes, physical oceanography, the thermodynamics of atmosphere over the atmospheric boundary layer and the marine boundary layer, synoptic meteorology, and human-induced seismicity. Now, Professor Naresh is also very actively involved in several sponsored projects that is funded by the Ministry of Earth Sciences, DST, ISRO, and also the climate change program of DST. Professor Naresh has published about 28 articles in peer-reviewed international journals, one book chapter, that is Progress in Tropical Cyclone Predictability and Present Status in the North Indian Ocean region. He has about 18 papers presented in national and international conferences. Also, he has a paper in October 2018, which was published in Nature Communications. So the paper is on seasonal modulation of deep, slow slip and earthquakes on the main Himalayan thrust. Now, Professor Naresh is also very actively involved in teaching both theory and practical subjects for the students at NIT Rourkela. So some of the theory subjects that is handling is on physics of atmosphere and ocean, introduction to atmosphere and ocean dynamics, physical and dynamical oceanography, modeling of oceanic processes, and climate science. So he has also conducted practicals on modeling and simulation laboratory, data analysis and visualization, graphical packages, and MATLAB programming, etc. He has guided 14 MSc students and 5 MTech students. He is also involved in administrative activities such as the Vice President of Games and Sports and the local organizing committee member for the centralized counseling for MSc and MTech admissions and outreach programs of the Institute. So with this brief introduction, it is my proud privilege to kindly invite our speaker for today, Professor Naresh, to deliver the talk. So it is a request that the questions and answer session will be attended after completing the talk, and the questions can be pasted in the chat box. Thank you very much. So now I go on to Naresh.
Sir, thank you very much for introduction, sir. Good morning, everyone. So today I'll be discussing about the topic tropical ocean and atmospheric interactions. We all know this is one of the important component of the climate system. So in this presentation, I'll be discussing about the various coupled systems such as tropical cyclones, equatorial waves, intraseasonal oscillations, where I will be discussing about the mid-season oscillations as well as Boreal summer intraseasonal oscillations. As a part of interannual variability, I'll be discussing about the ENSO and its dynamics, how the ENSO will be genesis and the different theories that are attributing for the ENSO I'll be discussing. At the end, I will be showing a case study how it is important to represent the ocean and atmosphere interaction in simulating the BSISO in a general circulation models. I'll be showing at the end. We know the tropical weather, the tropical climate is very much different from the mid-latitude and higher latitudes the climate. In terms of, in the tropics, we know that the Coriolis force is very weak and the pressure gradient force is also not so strong, except for the case of tropical cyclones where we have a strong pressure gradient force. And then the temperature variations are minimal. Here we have mostly homogeneous kind of a climate, whereas if you go to higher latitudes, we have the more contrasting frontal activity systems. And most of the weather systems associated with the tropics are non-frontal systems. The tropics atmospheric circulations consist of various temporal and spatial scales. If you can see that they're varying from the semi-diurnal systems to the decadal systems, such as for us AC interaction, the systems mostly important are the synoptic scale, starting from the synoptic scale, and quasi-biweekly oscillations also found to be very important in the AC interactions. And also intraseasonal oscillations is mostly driven by the AC interactions and the internal dynamics of the atmosphere. And then we have annual cycles, interannual cycles such as ENSO, Indian Ocean Dipole is very important, and how the AC interactions are playing a role. These things I'll be discussing in today's talk. The first is the synoptic scale, which has a tropical cyclone. The tropical cyclone is, you know, the time scale of the tropical cyclone will vary from few days to a week. We know in the Bay of Bengal, we have Bay of Bengal in the Northern Ocean. The tropical cyclone frequency is very high during 2 times, during pre-monsoon as well as monsoon season. Whereas, if you can see here, during monsoon season, we don't have much tropical cyclones because of the large wind shear, whereas this bimodal characteristic of a tropical cyclone's occurrence is one of the peculiar quality of any basin. And also, if you see the tropical cyclones, the number of tropical cyclones in the Arabian Sea and the Bay of Bengal, the number of tropical cyclones is generally high in the Bay of Bengal, very 5 to 6 times higher than the Arabian Sea. Whereas in the recent times, we are finding that the number of tropical cyclones in the Arabian Seas are increasing. These tropical cyclones are very one of the severe natural hazards, and it will cause severe destruction to the life as well as property. This is very important to understand and to forecast these tropical cyclones accurately. And we're thankful to the Indian Meteorological Department for its progress and predicting the tropical cyclones track and intensity very near accuracy and saving the many lives of our country. This year, 2021, we have a very 2 severe cyclones in the Arabian Sea as well as in the Bay of Bengal. This I'm showing for the Bay of Bengal, where you have a cyclone S before that taking a landfall captured by the Paradeep Doppler weather radar. We can see the structure of the tropical cyclone. Generally, you can see the tropical cyclone is an organized system. this organized conversion system, we have a different kind of a features. This kind of feature can be captured by a tropical weather radar. It can actually able to capture it. You can see the size of the tropical cyclones can vary up to some hundreds of kilometers. Sometimes it can able to cover the whole basin. Can impact, if it before the landfall, it can impact the many coastal areas, and it can cause a lot of storm surge and inundation in the low-lying areas. And further, it propagates in the land into the inland, and it can cause the severe rainfall, and it associated with strong winds. You can see the tropical cyclone on the right-hand side. You have a stronger winds compared to the left-hand side because of in the northern hemisphere, because of the Coriolis force and the movement of the tropical cyclones favoring for the strong currents, strong winds in the right-hand side of the tropical cyclone. So further we move. The tropical cyclone is an intense case of air-sea interactions. We all know that the ocean plays an important role for one of the necessary conditions for the genesis of a tropical cyclone, where the temperature should be higher than 26.5 up to the depth of 50 meters is one of the primary necessary conditions given long back by the Gray in 1968 about the tropical cyclone initiation. So how this Bay of Bengal and the Arabian Sea is favoring this? In general, the Arabian Sea and Bay of Bengal temperatures are generally warmer than is higher than the 26.5. So these conditions are mostly favoring. Whereas the atmospheric conditions are mostly plays an important role for the genesis of the tropical cyclones, such as the remnants that come from the South China Sea, and also the equatorial waves and the intraseasonal oscillations can initiate the tropical cyclones in this North Indian Ocean. We can see the oceanic conditions of the North Indian Ocean, whereas the climatology of the tropical cyclone heat potential is a metric that will tell us about the heat content of the ocean from surface to the isotherm of 26 isotherm. We can see that the units more than 60 kilojoule per centimeter square generally are favorable for the formation and the intensification of the tropical cyclones. If you can see in the Bay of Bengal, generally they are very higher. We can see in the recent cyclones which passes by the Ascendal, which is fabric, is moving towards the regions of higher TCHP, and we have a intensity. This is a tropical cyclone where one of the occurred in 2008 Nargis cyclone, which also got intensified, where that climatologically as well as synoptically we have a higher TCHP values. So in the ocean conditions, if you look for the ocean conditions, this ocean has consist of a semi-permanent kind of a rotating features. Those are called mesoscalities. We have two kinds of mesoscalities. One is the cyclonic and anticyclonic eddies. The anticyclonic eddies are generally warm. They are rotating in a clockwise direction, and they have and the downwelling process take place. Where suppose if a cyclone is propagating over these regions, it rapidly get intensified. This is the example for many cyclones. This is one of the shown for the 2003 cyclone and also for the Nargis cyclone. You can see many cyclones that when the cyclone propagate and it's encounter any kind of a warm eddy, it will get generally rapidly intensified. And also the AC interactions, if you look, the AC interaction generally happens in the primary eyewall zone as well as the secondary zone. That's the reason why the AC interactions are very dominant. The ocean provides a fuel these cyclones. It provides the heat in terms of the energy. It gains, the tropical cyclones gains energy from the ocean, and also the tropical cyclones impacts and momentum to the ocean. So it's an interaction. The very intense case of its interaction which takes place. We can see on if we look at for the monocyclone, we have seen that the right hand side and the left hand side, if we compare the enthalpy fluxes as well as latent heat fluxes, it is generally stronger on the right hand side. Generally, most of the tropical cyclones we can find the higher intensity of enthalpy fluxes on the right hand side. Whereas if you see the rainfall, it generally can be symmetric. Whereas if you have because of the wind shear, you can have on the left hand side the rainfall might be stronger. So what are the AC interactions that involve in a tropical cyclone? We'll see. So when a tropical cyclone passes, the first exchange of the heat that takes place from the ocean to the atmosphere, and also the momentum exchange takes place from and also freshwater flux takes place from the tropical cyclone to the ocean. When it encounters, when it goes, there are different processes that takes place. One such process is upwelling. Because of the winds, the cyclonic winds can cause a kind of upwelling features can lead to the sea surface cooling. If one such process is very important, it can determine whether the cyclone is going to intensify or decay. If the intensification, if the upwelling is more, then it can have a severe kind. It will impact negatively on the tropical cyclone. It depends to have an upwelling or the sea surface cooling depends upon the speed of the cyclone. The cyclone is moving rapidly. The ocean will respond ocean response will be very low. Whereas if the cyclone moves slowly, the response of the cyclone is very, very high, and then you can have a severe sea surface cooling. It can negatively affect the tropical cyclones. These are the various processes that involve in the Bay of Bengal. And also when the tropical cyclones propagate, there are different other processes that also important. One is that the mixed layer. The mixed layer is generally get deepened, get shallow. The deepening associated with the downwelling or as a vertical mixing, whereas the shallowing of the mixed layer associated with the upwelling. And also one peculiar feature of the Bay of Bengal, especially the Bay of Bengal, is that the presence of barrier layer. The presence of barrier layer is to the can have a different impact on the, especially on the upwelling as well as phytoplankton boom. When you don't have a barrier layer, the sea surface cooling will be more. It can negatively affect this tropical cyclone intensity can weaken. Whereas if you have when we have a barrier layer in the ocean, that will cause the tropical cyclone to it will not allow the upwelling to enter into the surface waters, so that it will control the heat. The tropical cyclone can further the sea surface cooling will be low and the can get intensified. That's why we can have found, if we observe the pre-monsoon cyclones and the post-monsoon cyclones, the intensity of the post-monsoon cyclones is generally high because of the presence of thick barrier layer, and also the enthalpy fluxes also very high in compared to the post-monsoon season. So these are the very important process that we're trying to understand. I think very important, especially for the prediction of intensity. The ocean plays a very important role for the prediction of intensity of the tropical cyclones, whereas the movement of this tropical cyclone primarily determined by the atmospheric motion. So these tropical cyclones can be affected by the different kind of features. Even genesis can take place by the different features. One such activity is equatorial waves. I'm going to discuss in detail about what are the equatorial waves and all. These equatorial waves, there are different kinds of equatorial waves, such as Kelvin, which is eastward propagating, and the equatorial Rossby wave. It can propagate the westward direction, and then we have a mixed Rossby gravity wave, which generally propagates in the westward direction. These waves can cause genesis of the tropical cyclone, especially in the Bay of Bengal as well as in the Pacific Ocean. So we will discuss how these waves can cause these tropical cyclones. What are these waves also? Not only these, recently even the work by inquiries people have addressed that the median oscillations and also plays an important role for the cause of the tropical cyclones, and also the ENSO condition. The ENSO conditions, Interannual IOD conditions, also plays an important role to have occurrence of the tropical cyclones. So what are those equatorial waves? The equatorial waves can be observed both in the atmosphere as well as in the ocean. These waves are very important. It controls the climate, the weather system of the particular region. It has a different frequency. For example, if you take the Rossby wave, generally propagates in the westward direction. You can observe from the satellite map of any OLR or any infrared radiation. If you observe, if you have observed a pair of twin vorticities, both high or else low on either side of the equator. Along the equator, they are symmetric. If you can observe this kind of a feature, they generally associated with, and the movement, if you observe the time, if they are propagating towards the westward direction, we can say they are associated with the Rossby wave. These waves can travel with the different speeds. In the atmosphere, they travel at the speed of nearly 5 to 7, generally moist, they travel at the speed of 5 to 7 meters per second, whereas in the ocean, they travel very slow, they travel at the speed of less than a meter per second. Similarly, we have a Kelvin wave. These Kelvin waves are the equatorial travel waves. These Kelvin waves travels only in the eastward direction. We also have a similar kind of oscillation, that is intraseasonal oscillation MJO. I was going to tell what is the difference between the Kelvin wave and the MJO. These waves can travel in the atmosphere. They travel very fastly. In the ocean also, they travel at a speed of very high compared to the Rossby wave. They travels only in the eastward direction. Whereas we have another kind of a wave, that is a mixed Rossby wave, which can travel both eastward and westward. Mostly westward is the most prominent one. We have a drive Rossby wave as well as convective Rossby wave. The speed of the convective one generally slower. These kind of features occur in the quasi-biweekly oscillations as well as comes under the subseasonal, intraseasonal oscillations. So these waves have a different kind of restoring forces. For example, if we take the Rossby wave, the restoring force of the Rossby wave is the conservation of the potential vorticity. That's the main component why we have this kind of a feature. And also, if you come to the Kelvin wave is a special kind of a gravity wave, it has to be the stratification has to get balanced, and also the variation of the Coriolis force along the side of the equator, that plays an important role. We have this kind of a Kelvin wave. This is a one kind of a Kelvin wave. There is another kind of a Kelvin wave, that is a coastal Kelvin wave, which occurs in the different coastal beaches, the oceanic component. It can be traveled by the coastal wave. Though here I'm going to focus about the we'll discuss about the equatorial Kelvin wave. Whereas mixed rotary wave, it's both the gravity as well as the Coriolis force are the restoring forces to have this kind of effect. So how do we find these waves? How can we identify these waves in a spatial scale? For that, we have to apply the mechanism proposed by the Wheeler and Kildas in 2004. We proposed a wave number frequency. Using that, we can able to identify those waves from the OLR data as well as from the sea surface height anomalies data. This is the data we have taken from the OLR data long-term climatology over the Indian subcontinent. We can see here over the Indian Ocean. We can see this, the propagation of a different waves. We can able to identify those waves at the different wave numbers and frequency. This is for the symmetric waves and the non-symmetric waves. So I'm going to tell a little theory about this, how these waves are evolved and how we understand. This is a famous work done by Martinso in 1960. He proposed this kind of a waves by solving the shallow water equations. When he solved the shallow water equations and we come up with a solution, horizontal dispersion relation, using this, he able to identify different waves that able to see in nature. Mathematically, this is the equation tells about understand about this kind of waves. So these waves, if you look these waves, they have the positive and the negative k values. The positive values represent they are propagating in the eastward direction. The negative values represent they are propagating in the westward direction. We have a different frequencies. The frequencies vary from 1 to 4, the lower frequency waves and the higher frequency waves. In general, if you observe this from the satellite data, they generally which are the high frequency waves, which has a periodicity shorter than 1.26, generally comes under category of inertial gravity waves, which is also called as Poincare waves. And we have a long frequency waves, which are having the periodicity greater than 7.3 days. We can able to see these kind of waves. So what are these waves? We'll look into. This first one is the inertial gravity waves, or else Poincare waves. They travel very fastly. They can disturb the weather of particular equatorial places and the tropical places. Okay, they travel in the both eastward and westward direction. If you can look here, they both travel in the eastward and different modes. They can travel in the both eastward and westward direction. Whereas at the lower wave number, they behave like a dispersive wave. At the higher wave number, that means higher wave number means those waves are very short. Those wavelengths are very short. Whereas the lower wave number means the waves are long. And they behave like a dispersive wave. So what the dispersive wave is such that the phase velocity and the group velocity can be in opposite direction, can have a different magnitudes. The dispersive wave, it depends. The speed of the wave depends upon its frequency as well as wave. Whereas when it's a non-dispersive, the phase velocity, the group velocity, both will be same, does not depend upon its frequency. This the inertial gravity waves, at long waves, they behave like a non-dispersive. Short waves, they behave like a dispersive. Long waves, they behave like non-dispersive. If it comes to the other waves, which is the other one, which is the Kelvin wave, which is a special category wave. It is non-dispersive wave. It does not depend upon the frequency of the wave. It always propagates in the eastward direction. So we have other kind of a wave that is the most important one, which affects the tropical climate in the North Indian Ocean. That is the equatorial Rossby wave. These equatorial Rossby waves generally propagates in the westward direction. The wave numbers are generally, we can find that we can have a single wave. The single wave means can cover the whole envelope of the equator. Those kind of waves are generally behaves as a non-dispersive. Whereas when it goes to the shorter waves, when you have many waves, 3-4 waves, then behaves like a dispersive. These waves, the phase velocity, the group velocity, the phase velocity is always can be westward direction. The group velocity can be eastward and the westward direction. These are the waves. And if we compare the speeds of those waves, generally the Rossby waves are generally slower compared to the Kelvin waves, whereas inertial gravity waves are generally very quick waves. So these are the waves into very important. These waves plays an important role for the intraseasonal oscillations in the ocean. These waves are very important for the interannual variations. So I'm going to show how these waves are important for both for the intraseasonal as well as for the interannual variations. Okay. When it comes to the intraseasonal oscillations, the tropical intraseasonal oscillations is one of the dominant mode of the tropical climate system. we have two different kind of intraseasonal oscillations. One is the Boreal summer intraseasonal oscillation, which occurs during time of May to October, generally propagates in the northward direction, northeastward direction. This only prevails only to the Indian subcontinent and as well as the northwest Pacific region. Whereas we have which is throughout the year we have this other kind of intraseasonal oscillation that is called median oscillations, which was discovered in 1971 by Medin and Julian by observing the data over the east coast of the Africa. They able to observe this kind of data in terms of radiosonic data. They're able to identify this kind of oscillations. Okay, so what are these intraseasonal oscillations? The median oscillations, they propagate along the equator in the eastward direction. It can influence the climate, and the weather of a tropical places. Recently, the monsoon has a very good relation with the median oscillation, especially the onset dates. The onset of the monsoon is generally associated with the phase of median oscillations. And also, we have seen from our study that these intraseasonal oscillations can impact the diurnal cycle. The diurnal cycle of the intraseasonal, when the MJO is propagating, when it's over the Indian Ocean, we have a very strong amount of the frequency of the very strong intensity of the kind of a diurnal cycle of rainfall. Whereas when it's over the suppressed phase, that means when it's moved over the Pacific region, though the diurnal cycle is not getting affected, the frequency is not getting affected, but the intensity of the rainfall is being affected. And also the estimated rainfall events up to the 20 degrees north. This when it's propagating over the Indian Ocean, it can influence the many kind of estimes, and also cyclones, depressions. They are all being affected by when it's the MJO situated over the Indian Ocean. Not only that, recently work by the IHM, they have shown that when we have this kind of a median oscillations, it also can affect the fast fires in the California work done by the fluxes, and they have shown that how these affect the different kind of features. How the structure of the intraseasonal oscillation looks like. They look like that when this propagating in the eastward direction, it associated with a strong deep convection. We have a pair of anticyclonic and the cyclonic vortices you can see in the atmosphere. In the low level, we have a cyclonic vortices. In the upper level, we have an anticyclonic vortices, and the pair of it will further propagate in the eastward direction. If you look at the center, if you look at the 500 hectopascal, we have a updrafts. We generally associate with the updrafts and the winds. The main signal we can observe if you have any kind of a scatterometer winds, as well as any kind of a satellite data, we can able to observe that the winds that generally associate with the propagating in the westerly winds. We can observe the westerly winds in the Indian Ocean. Whenever we have the convective centers that propagating, we can able to see the westerly winds or it tells about the propagation of the convection of MJO. Similarly, and what the scale of this MJO associated? The scale associated is the planetary scale can have up to 5,000 to 10,000 kilometers. Recently worked by the Hunt also shown that even the propagation of median oscillations can also influence the subtropical weather and also the western disturbances during time of the boreal winter. They also have the higher frequency when the MJO is oscillating over the Indian Ocean. What is the speed? What is the speed it propagates? It propagates at the speed of 5 meters per second. In generally, we have a similar kind of a convection that also propagates in the eastward direction along the equator. That is the Kelvin wave. The Kelvin wave, but the difference between the Kelvin wave and the MJO is basically comes in terms of the speed. The speed of the Kelvin wave is very high. Generally, the convective Kelvin wave propagates at a speed of 10 meters per second, whereas the MJO propagates only at a speed of 5 meters per second. If you look for this is the work done by the Nakazawa in 1980 using the satellite data, using high resolution satellite data, you're able to identify what are the structure of the cloud looks like into the median oscillations. If you look at the structure of the cloud, this kind of median oscillations, though as a supercluster, it is moving in the westward direction, the eastward direction. If you look inside each cluster, we have a different kind of oscillation that will propagate in the westward direction. So that means it confirms that these kind of oscillations, these kind of median oscillations associated with both the propagation of Kelvin wave as well as conveyed to Kelvin wave as well as conveyed to the Rossby wave. The recent work done by IRC group, they have shown that when these median oscillations interacting over the maritime continent during time of summer monsoon, they will reverse as a conveyed to Rossby wave lobe, and they will interact with the central India, and they will cause the the rainfall over the central India. This is one of the pioneer work done, how this interaction between the meridian oscillation propagation and influence on the monsoon trough region. Further, so here I'm going to demonstrate how a Kelvin wave, with the help of the Kelvin wave, I'm going to demonstrate how this MJO propagates in the eastward direction. Suppose we have a kind of a convective cell. When you have a low pressure systems on the eastern side, and the western side, suppose you have a high pressure systems along the equator. So how these meridian oscillations can propagate in the eastward direction, we'll try to look into. So when you have this kind of feature, so what happens because of along the equator, the winds converges from high pressure to wind converges from the high pressure, that is from the western side to the eastern side. We have a convergence of the winds. But along, if you just move away from the equator, you can have the Coriolis force comes into feature. When the Coriolis force causing these winds, when these winds are westerly winds along the northern hemisphere, because of the deflection, it will turn towards along the equator. Similarly, in the southern hemisphere, the deflection is towards the left side. It causes the cause of a convergence. With the time, you will have a kind of a wavy feature, so that what we will see that once we have a low pressure and high pressure, after some time, eventually with the time, in between the high pressure and low pressure, especially in the western side of a low pressure, you have a new high pressure cell, and the eastern side of it, you have a low convergence cell. With the time, we can observe that it propagates like a wave in these convective centers propagate for a wave in the eastward direction. This is the similar kind of mechanism we can also observe for the dry Kelvin as well as moist wave, whereas the speed of the Kelvin waves are very high compared to the meridian oscillations. Then what is the role of the AC interactions in these kind of mechanisms that will help us sustain as well as progress of these kind of meridian oscillations? One such mechanism is that the sea surface temperature. The sea surface temperature plays an important role, because the evaporation, the surface temperature, energy transfer from the ocean to the atmosphere, that's a very important component to have any kind of a convection. When the convection initiated, when the convection initiated, before the main convection, you should have a warm SSTs. Because of the warm SSTs, especially prior to the occurrence of a MJO, 10 days prior to this, we will have a very strong SSTs that can cause us the cumulus convection. This cumulus convection, with the time, what happens is that with the time they will become the more cumulonimbus cloud. At the time, you will not have any kind of SST anomaly. Eventually, with the time, it will become a colder SSTs. The exchange of the heat, that's a primary thing to have this kind of a convection. It associated with different kind of a clouds, cumulus to cumulonimbus clouds. Their growth plays an important role, and the specific humidity is very, very high. This kind of meridian oscillations can impact both the tropical weather of southern hemisphere, northern hemisphere, up to the 10 to 15 degrees north and south. Okay, so this is how this tropical cyclone, these meridian oscillations can have this kind of research mechanism help us to propagate the eastward direction. So that's about the meridian oscillation. We have another kind of a oscillation which only prevails from the May to October, that is the Boreal summer intraseasonal oscillations. Unlike the meridian oscillations, it propagates throughout a year, and as well as it about eastward direction. It propagates in the eastward, primarily in the northeastward direction. These recently studies shown that these Boreal summer intraseasonal oscillations plays an important role to have the active and the break spells in the Indian summer monsoon season. So it generally initiates over the Western Indian Ocean and further propagates into the Bay of Bengal, and further propagates into the China. We have this kind of a cell. So how it is propagating? To understand this kind of structure, so how the AC interactions plays an important role for the propagation of this kind of a oscillation. You will see. This is the phase relations between the AC fluxes during the MJO. So as I said earlier, initially for the recharge-discharge mechanism also. So prior to the onset of a MJO, we need to have a very warm SSTs. So if we compare the phase relation between the SSTs as well as with the convection, the deep convection, the SSTs generally lead the deep convection in terms of 5 to 6 days. 5 to 6 days, we should have a warmer SSTs that releases a lot of the heat, latent heat flux, central heat flux into the atmosphere, causes the convection. Once we have a convection initiated, when the convection initiated, it causes a it covers the cloud cover will be there. There will be the short wave radiation will be suppressed. You will have a net heat flux will be negative when the convection is strong. When the convection is very active, during that time you will have a net heat flux system. So afterwards, you will get again further decay. Will move towards the other region. What happens is that we have again the sun will be there, the fair weather conditions over the ocean. Again, you will have a warmer conditions. The wind stress will be weakened. The net heat flux will be latent heat flux will be decreased. The net heat flux will be positive. With this mechanism, it is able to the kind of a cycle. It will recharge and discharge the kind of a AC fluxes plays an important role for the propagation of the convergent oscillations. Though the movement of the MJO is mostly associated with the internal dynamics of the atmosphere, whereas the strength is determined by the oceanic conditions. Similarly, for the BSISO, Boreal Interannual oscillations, when you have this kind of convection, how it's moving from the southward to, whereas the MJO is from the west to eastward, whereas from the south to northward, how it's propagating is at the similar kind of conditions. Prior to the convection, we should have a kind of a easterlies. When you have easterlies, and the ocean conditions should be warmer. And the latent heat flux, more static energy will be very positive. Those conditions providing for the deep convection. With the time, eventually, when it's moving further towards the northward direction, you will find this kind of a westerly winds, and you have a negative anomalies of the latent heat flux, as well as the sea surface temperatures also will be negative. So these features we try to see with kind of a. So we made an attempt. My student Konda Gopinath made an attempt to understand how these MJO AC interactions over the Indian subcontinent and the BSISO AC interactions can have a different features are associated. When it comes to the mid-Indian oscillations, we can see when you have mid-Indian oscillations propagating over the Indian subcontinent, we have found that over the North Indian Ocean, we have found the warmer conditions and the winds are generally easterly winds. Whereas along the equator, we have a westerly winds, and during the time of the passage of the active MJO, we have a negative SST anomalies, whereas in the northern hemisphere, Northern Indian Ocean, we have a different kind of a contrasting features. The conditions prevail during time of the monsoon season when the MJO is propagating over the Indian subcontinent. When it comes to the BSISO, and when you have a BSISO, the strong BSISO, when you have a strong active BSISO propagating in the northward direction during that time, generally winds are associated over the Arabian Sea or westerly. Over the Equatorial Indian Ocean, we have a easterly winds, and prior to the passage of the BSISO, we have the warmer SSTs, whereas during the active BSISO time, we have a negative SST anomalies. These are the features we are able to observe using the different kind of a satellite and the model outputs. We are able to see these kind of features for the both for the MJO and the BSISO. This is about the Intraseasonal oscillations. Then comes to interannual variations. The interannual variations, which has we have a different kind of interannual variations, that is Indian Ocean dipole and El Nino and southern oscillations. Okay, these are the primary, and Atlantic Nino is a recent one. Many works I think people are doing the Atlantic Nino also. So what is the interannual variations? How AC interactions are important for the interannual variations, for the sustenance and the propagation of these interannual variations we'll see. So this we will first discuss about the normal conditions for the Pacific Ocean. Along the Equatorial Pacific Ocean, we can see that generally the winds are easterly winds. When you have easterly winds along the surface, it will cause us the upwelling in the southeastern Pacific Ocean, whereas it carries the warm waters. It carries the warm waters from the east to west, and the warm waters will be piled up there, and the thermocline will be deeper. We have intense convection over the Indian Ocean or the Western Pacific Ocean. We have this kind of circulation. This is called the Walker circulation. These are normal conditions we have during time of normal conditions. Once the El Nino initiated, there are different theories how an ENSO will be initiated. There are stochastic theories, naturally the different theories will be able to explain, and a wind burst can cause a El Nino, different kind of a condition, different theories help us to understand why El Nino will be initiated. Once we have a El Nino initiated, the major thing we will find is that the changes in the wind. The winds instead of becomes the west easterly winds becomes weakened, and if we see the anomalies, we'll have a westerly wind anomalies. Slowly, the warm waters migrate from the western side to the eastern side. The thermocline will be get deeper, and the upwelling, basically it affects the upwelling, and the convective centers get shifted from the Eastern Pacific Ocean, the Western Pacific Ocean to the Central Pacific Ocean. This is the primary changes we'll be able to observe during time of El Nino conditions. And as we have intense case of normal conditions, that is the La Nina conditions. La Nina conditions, what happens is that the trade winds get strengthened, and you have a very severe upwelling in the Southeastern Pacific Ocean and the very warming. It's an Indian Ocean warm pole region. Indian Pacific warm pole region, it gets more strengthened, and you have a very intense convection during time of these phases. We have, this is the opposite phase of El Nino, is on the strengthening of normal conditions we have in La Nina conditions. How air-sea interactions plays a role? What are the different theories to understand this kind of ENSO features? And we can able to observe these kind of features using the Hormel diagram. We can able to identify the dominant modes of different oscillations. In general, we will find along the Eastern Pacific, along the equator, we have a cold features. These are the seasonal changes we find. But whereas if we found these are the zones where we have a strong warm anomalies over the Eastern Pacific. These are associated with the strong El Ninos. We have a strong El Nino in the 1918, 96 and 97, 98. This is the strong El Nino region, and we have recently to the 15-16 strong El Nino. And also we can see the strong La Nina features. You can observe the 98 and 99. And generally these are El Nino generally followed correct by La Nina. We have features. And the other thing is that there is asymmetry between the El Nino and La Nina. Generally, the duration of the El Nino will be shorter compared to the La Nina. The La Nina duration will be generally longer. So we will see what are the different theories that help us to understand the El Nino. The famous theory is the proposed by Jerkins. Jerkins proposed this theory. This is the positive feedback mechanism, how the ENSO can be initiated. The first you have, when you have a warm SST anomaly in the Eastern Central Pacific, because of the weakening of easterlies. When you have a weakening of easterlies, it will weaken the, first we can see is that there is a changes in the water circulation. The water circulation along the surface, we will see that the easterly winds becomes weakened and further becomes westerlies. That's a major change we will find. When it becomes further weakened, when it further weakens, the thermocline will be deeper on the eastern side, and the difference between the eastern and the western will be nullified, and we will also have the warm waters that accumulate in the eastern side, and slowly the thermocline will be, the anomalies of the thermocline will be balanced. And then further, if the cycle further goes on, it will further causes the equatorial upwelling on the eastern side, western side, and whereas in the warming on the eastern side. But this is the theory help us to understand the positive feedback mechanism, but there is no negative feedback mechanism. So once we have El Nino, this theory helps us to, it tells us it is continuously grows. The SSTs in the Central Pacific and the Eastern Pacific, it continuously grows, whereas there is no decay mechanism. There is failed to explain the decay mechanism of why the ENSO will be fail. So later, there are different theories. Delayed oscillator, this is one of the important theory. Help us to understand how once we have a El Nino initiation, how this will be weakened, and we have a La Nina condition. This can be understood by using this delayed oscillator theory. So when we have a westerlies, the westerlies can be when you have a westerly wind burst over the Central Pacific region, it causes a different kind of waves, oceanic waves. That is the Kelvin wave and the Rossby wave. The Kelvin wave will be propagating in the eastward direction, which is a downwelling Kelvin wave. When the downwelling Kelvin wave propagates over the ocean, it causes the warmer SSTs, whereas it also causes the Rossby wave, upwelling Rossby wave. And the upwelling Rossby wave generally propagates in the westward direction. The upwelling Rossby wave can cause the cooling of the sea surface conditions. When both waves travel originate from the Central Pacific, they travel at different directions. Okay. When they travel at different directions, where's the difference is that the speed of the Kelvin and Rossby wave. In the ocean, the speed of the Kelvin wave is about nearly 3 meters per second, whereas the Rossby wave is only less than a meter per second. So that's the major cause. Why do we have at this again? We have a La Nina condition, and the asymmetry of the El Nino and the La Nina in terms of the duration can be understood by the movement of those waves. These waves propagate when they propagate in the eastward direction from the Central Pacific, causes the ocean condition in the Eastern Pacific will be warmer, the thermocline will be deeper. Similarly, the Rossby wave will be propagating in the Central Pacific towards the Western Pacific Ocean. So still it will be traveling. It will slowly causes the sea surface temperature. When the second wave initiates, the westerlies will, when we have a strong westerly wind burst, we have a second initiation of the Kelvin wave. This Kelvin wave propagates, it will try to reverse. When you try to reverse, it reverse as it will reflect from the Eastern Pacific and reflect as the downwelling Rossby wave. whereas this Rossby wave reflect from the Western Pacific and reflect as a upwelling Kelvin wave. When these waves interaction happens, this will get again cause of a this kind of these El Nino conditions can changes to the La Nina conditions. That the duration of the La Nina will be generally stronger. But this theory will not explain about what happens to the subsurface features of how the thermocline changes will be explained, and how the transport of the water from the equator to the tropics couldn't explain by this theory. But this can be explained by the Recharge-discharge theory. This Recharge-discharge theory is different from the MJO. Here there is this recharge-discharge theory, we can able to understand how the transport of the water from the surface and the surface takes place. At the surface, when you have a warm SST anomalies caused by the westerly winds, that causes when you have a warm SST anomalies that causes at the surface. At the surface, because of the equine transport on the other side of the equator, the water will be converging. That causes the deepening of the thermocline, and the SSTs will be warmer. But this water has to get diverged at the bottom. At the bottom below the thermocline, we will have a swept-up transport which is diverging at the bottom. That causes with the time, it becomes again nullify the depth anomaly, the thermocline depth anomaly again nullify when the wind speed will be less. Again, the SST anomaly will be further nullified. And when you have a strong easterly winds, that causes the La Nina conditions. During those times, what happens is that at the surface, there is a divergence, equine transfer, there is a divergence, more cooling takes place. But at the surface, when you have a divergence at the surface, you need to have a convergence at the bottom, where the swept-up transport contributes the warm waters. That again, eventually with the time, you will have again the no temperature anomalies, as well as the wind stress will be also get nullified. This is the cycle to help us to understand how the El Nino will be recharged and then discharged during time of the La Nina conditions, and then again the cycle will be continued. So, but this theory couldn't consider the waves, the motion of the Kelvin waves and Rossby couldn't incorporate those features. So both together, considering this unified oscillator theory, can able to understand. But combining both the reflection of the Kelvin wave and the Rossby wave, as well as the spectrum transport on below the thermocline, can able to explain about these kind of features. So this ENSO is mostly involved in it's a very prominent ocean atmosphere interaction, plays an important role for the sustain. It can have a severe impacts on many weather and climate, especially in summer monsoon season. When you have a ENSO conditions, El Nino conditions, we will have a drought conditions. When you have a La Nina, we will have very flood conditions over there. So we need to predict in advance how these El Nino feature ENSO conditions will be there. Similarly, so we try to see in a Boreal summer interseasonal oscillations how the CMIP models able to simulate the Boreal summer interseasonal oscillations, and what is the role of the oceanic interactions, and how it plays a role to have this kind of the accurate Boreal summer interseasonal oscillation simulations we have seen. Further, we have studied the bias. We have seen the bias of the different models with respect to observations. We have considered 22 CMIP models where the availability of the data for the latent heat first, temperature, and the winds is available. So we have seen all these models, how these models are showing the bias. You can observe over the ocean generally, or the ocean they are generally overestimating, or the land they are underestimating. This is a common feature observed in all the models, most of the models, as well as the wind stress. Also, we have anomalies in the wind stress compared to all the models. When you compare we consider all the good models based upon by using the Taylor analysis, we are able to identify the good models, and we found the ensemble mixed multimodal anomalies. We have found that the bias is reduced when you consider all the good models. Similarly, these models, how it simulate the northward propagation of a BSISO. This is the general in observations. We can see that how the BSISO will be propagating the northward direction. We can see here. So we generally, when it's propagating the northward direction, the winds are associated with easterly. After that, we have a westerly winds. That means the westerly winds lag the deep convection when this BSISO takes place. So these are the general features we need to observe over the Indians. This is for the Arabian Sea. How these features need to be shown by the different models. When you see these models, how they are played, many models are showing decent goods. Miro C5 and the Miro CKM, they are more these models, and GFL models have done a good job, whereas IPSL models and other and IPSL models and MRI models are unable to show these kind of significant features. We are trying to investigate why these models fail represent certain kind of features, why the other models able to show this kind of prominent features. When you try to see, when we try to understand using the phase relation between the SST and precipitation, we are trying to see, we have seen for the Arabian Sea, Bay of Bengal, and North Indian Ocean. When you look for the North Indian Ocean, using the observations and the SST and precipitation, where the negative values represents this SST is leading and the positive values represent the precipitation is leading. When you see the correlation between the SST and the precipitation over the Arabian Sea, we can find that SST is leading at the 5 days. The SST is leading at the 5 days to the precipitation. That means when you have before the conversion of 5 days, you have a warmer SST and followed by the good amount of rainfall. The correlation is about nearly 0.5. Some of the models which what we are seeing the propagation, those models able to show the good phase relation, where the models which are failed to show the northward propagation, they completely fail to show this kind of features for the different oceans. Similarly, in the Bay of Bengal, we have seen the correlation between the SST and precipitation. Whereas compared to the Bay of Bengal and Arabian Sea, the Arabian Sea response is very quick, where the lag is only 5 days. Whereas when you found the peak correlation, it's only 10 days, 10 to 12 days. It means here before the 10 to 12 days, we have a warmer SSTs, and then we have followed by the northward propagation of the convection. Though the correlation is not as strong compared to the Bay of Bengal, but the models fail, we can able to determine why these models fail using this. Okay. The other feature is that when you compare the whole North Indian Ocean, we are able to see the similar kind of features. Similarly, we try to see the wind as well as precipitation. Here we found that the Arabian Sea, Bay of Bengal, as well as the Indian subcontinent and North Indian Ocean, one of the prominent thing was that the westerly winds generally lag. Generally lag to the precipitation about 4 to 5 days over the Indian Ocean, North Indian Ocean, as well as in the subcontinent. These are the features, and we be able to determine why these models fail. We try to found each model how the different kind of mechanisms, different phase relations are important to determine the strength. The correlations in the observations, we try to compare the observations. What is the correlation? Some of the models are showing the stronger correlation, some of the models are showing the pure correlation. The major difference what we found is the phase values what you found in the observations. The models which have failed are showing that large bias in the phase relations. That's the primary reason why these models fail. We are able to see. Similarly, what we are doing for the CMIP 6, I think we have found that by incorporating more static energy, we are able to understand why this CMIP model, how good able to simulate the BSISO 6, BSISO, and then the AC interactions, how they represent, we are seeing. So in a nutshell, the ocean air-sea interactions are generally at high frequency. Once when you have a high frequency of the air-sea interactions by equatorial waves or some kind of tropical cyclones, afterwards the ocean keeps its memory and can modulate different kind of low frequency oscillations, such as intraseasonal oscillations and the long-term interannual variations. These are how both, though the tropical climate system, these scales occur at different time scales, spatial scales, but they are constantly interact each other. Everything is important to have this kind of oscillations. So AC interactions, we need to have more observations in the Bay of Bengal and Arabian Sea to monitor these kind of AC interactions, and very high resolution observations will be required, as well as the boundary layer measurements will also required for the North Indian Ocean to understand improve understanding of the AC interactions to be done. Okay, so I would like to thank everyone for attending, for your kind attention, and also I would like to thank the Ocean Society of India for giving this opportunity to present this work. Personally, I would like to thank Professor Kumar Bhaskar for giving this opportunity. Also, I would like to thank NCPO for hosting this talk. Thank you very much for attending. If you have any questions, you can ask me here, or else you can write to me to the email. I'm happy to answer your questions. Thank you. Thank you very much.
So thank you, Professor Naresh, for a very interesting and it was a very, very interesting presentation. You have just covered actually almost all the aspects of the tropical and ocean interaction. It's very, very important actually that these studies are really very important. So let me go to the chat box. Let me see that is there any questions on the chat box.
I think
I don't find any questions being put on the chat box so far. Yeah, I would just like to ask you one question about you have actually made a comparison of the different models which are in CMIP 5, CMIP 5 family of models, and then you are comparing with observations, and you mentioned that Miroc C5 and the GFDL models, they show a good resemblance with the observations. Right? Have you made any comparison of the CMIP 6 family actually? CMIP, because the quality, what I understand is CMIP 6, there are the same model basically was showing a better quality in CMIP 6 as compared with CMIP 5.
Yes, sir. We have communicated this work and we have done the comparison of CMIP 6 models. We have considered nearly 26 models. We have shown that I think CMIP GFDL models and Miro 6. Miro 6 also doing good in CMIP 6 simulations.
Yeah, because that is a very interesting observation, because what we find also this Miroc C5 and of course Miroc C6 as what you said, these are basically the models from the Japanese meteorological agency. So I think these models have been consistently performing better actually, not only for the precipitation, but we are also finding it for the wind speed. The wind speed and other surface parameters, these models are outperforming the other models actually.
Good, sir. Good, sir.
Yeah, that's a good observation. Yeah.
I am not seeing any questions.
I think Dr. Balasubramaniam actually he said that I have a specific question. Let me see what is the question actually. Yeah. So I'm just waiting for the question. I think so far. Yeah, I think Dr. D. Balasubramaniam from the Space Physics Laboratory, VSSC, he actually put a question on the CD parameterization. The question is, at high wind speed, what is your view? How good we are presently at the drag coefficient parameterization at high wind speed? What can be done to improve it?
Yes, sir. That's a very important and good question, sir. I think drag coefficient is still we need to have high quality observation. The sonic observations will be required to really check the drag coefficient features. At high wind speeds, I think as we generally following that bulk aerodynamic method as well as covariance method. In the drag speed, high wind speed, they are generally okay up to the certain limit. Beyond that, I think the work done by you also, I think published with Natural Hazards, shown that how the drag wind speeds are after a certain limit of the wind speeds is not able to show much variation. I think still we require more efforts, not in Ocean, to better understanding in the how the drag wind speeds vary. I think need to explain. I think the bubble. I think the bubble experiment now is going on. I think they are doing on the AC interaction. I think they may come up with more clear understanding in the real time how the drag coefficient will vary in the ocean.
So I think there's the same another question by Dr. D. Balasubramaniam. His question is, in the models, we depend on the drag coefficient for air-sea exchange processes. At high wind speed, we don't have many observations. So how can we improve it?
So the parameterizations of the boundary layer, I think that portion need to be improved. That's a very good question, and they need to be focused on that topic how the models are represented. Drag coefficient, the realistic drag coefficient, that coefficient still lacking. The models are lacking. That's why the models failing to show
the list provided to director
interactions.
to find the best.
Okay, that's a good observation.
Yeah. There is one more question.
Repeat all the.
There's one more question from Gokul Tamil Selvam. This question is, what could be the role of potential vorticity conservation in generation of anomalous cyclonic circulation symmetric about equator, located to the northwest and southwest of diabatic heating?
What could be the role of potential vorticity conservation in generating the anomalous cyclonic system along the system, located in the northwest and southwest diabatic? So I think this is very diabatic heating proposed by the Gill model. The Gill model, if you study the Gill model, that able to explain how this conservation of potential vorticity can generate a different kind of waves. I think basically the Gill model tells about how diabatic heating and this potential vorticity conservation takes place, how to get generated waves. Right. You can able to understand by this by using understanding the Rossby waves. When along the Rossby waves, you have both cyclonic and anticyclonic vorticity. Because of the when it's conservation of potential vorticity only, if you're able to understand that it is propagating in the westward direction. I hope I answered the question. If further clarification can be found by reading about the Gill model. Gill model is famously used. It's a kind of a diabatic heating. If you incorporate in the ocean, it can causes atmospheric waves that propagate the eastward direction Kelvin waves and the westward propagating Rossby waves. From that we can able to understand those features.
So, thank you. I think there is one more question by Mahendra.
Yes, sir, please.
So he said it is a nice talk. And what would be the most important factors triggering active BSISO during recent years?
The BSISO is there. BSISO is there. We identified, I think, from 90s, but BSISO exists since the month. We are months and BSISO is there. What are the triggering mechanisms? The triggering mechanisms is generally it's very different theories tells like MJO also. What causes this kind of a triggering mechanisms is a stochastic natural variability that occurs mostly in the Western Indian Ocean. That's one of the thing. And when you have this kind of a waves, the westerly wind burst in the ocean also can causes this kind of mechanisms. But still, we haven't fully understand how these intraseasonal oscillations will be initiated. I think that's need to be understood.
Yes, yes, I think I agree with it. Yeah. Let me see. I think there are no more questions. So I think there are no more questions in the chat box. So on behalf of the Ocean Society of India, I thank you very much for this very interesting talk. And of course, as what you said, there are many things to be understood, and it's a very important topic that we need to look into much detail. So thank you very much from Ocean Society of India. I thank you very much for this very excellent talk.
Thank you, sir. Thank you very much for giving this opportunity. Thank you, sir. Thank you very much. Thank you all the audience to attend. Thank you, sir.
Thank you.